For this video, I want to go over head recursion. If a recursive call is the first statement in a recursive function, then it is referred to as a head recursion. Let's take a look at this function starting on line 16. If you take a look at line 21, our first statement is a recursive call. There is no statement or operation before the call, and so the function doesn't have to process or perform any operation at call time. Therefore, all operations are done at runtime. Let's go ahead and trace this function. So what I'd like to do is, on the right hand side where you see the blue canvas, I want to start off by creating a stack. Let's just say that this white canvas is our stack frame. And if you take a look at our main function, we call head recursion. How this works is an activation record is created for main once the compiler reaches line 8. And inside of main, we call head recursion. And I'm going to abbreviate head recursion to HR. And every time our recursive function is called, or anytime a function is called, an activation record is created. So we go to line 16. When we enter the function, we go to line 18 and check to see if this condition is met. Is data greater than 0? And in this case, the answer is yes, 3 is greater than 0. And so we go to our recursive call on line 21, and again, we call our function. And every time we call our function, an activation record is created. So HR3 calls the function HR3 minus 1, HR2. And when it calls HR2, an activation record is created. So again, we go to line 16. And on line 16, we go down to line 18. And it's 2 greater than 0. And the answer is yes, so this is a true statement. We go to line 21. A recursive call is made, and so an activation record will be created for it. 2 minus 1, that gives us HR1. Anytime a recursive function is called, an activation record is created. So this becomes HR1. So we go back to our function on line 16. We go to line 18. Is 1 greater than 0? That is a true statement. Head recursion function is called again. 1 minus 1 is 0. So we go back to line 16. And again, an activation record is created for head recursion 0. And then we go to line 18. Is 0 greater than 0? The answer is no. And so we don't enter this if condition. Therefore, this function, HR0, is popped off the stack frame. And once that is popped off the stack frame, the call returns to HR1. It resumes back to line 22 where we print the data. We have a print data, and I'll just abbreviate P for print. And let me put the output here. The data is printed. We're printing 1. And once line 22 is executed, there are no more operations or statements after line 22. And so this function is completed and it terminates. So HR1 is popped off the stack. The call then returns back to HR2 function, and it resumes at line 22. On line 22, we are printing data. And in this case, we're printing 2. And after line 22, the function is executed and completed, and HR2 is popped off the stack. The function call then returns back to HR3. HR3 resumes on line 22. Again, we are printing our data. And after line 22, there are no more statements or operations. And so this function is completed and is therefore popped off the stack. And so the call returns back to main. And once main gets to line 12 where it says return 0, then main is popped off the stack. But let me run this. And there is our output 1, 2, and 3. Now let's create a tree to trace this function. And so we go to main and head recursion function is called. And again, I'm going to abbreviate it to HR for head recursion. We go into the function on line 16, and on line 18, is 3 greater than 0? And the answer is yes. And so we go down to line 21. Again, we call the head recursion with the data minus 1. 3 minus 1, that becomes 2. We go back to line 16, and then we get inside the function. Is 2 greater than 0? Yes. And so we call the function again. And 2 minus 1, this becomes HR1. And so we go back to line 16, onto line 18. Is 1 greater than 0? Yes. and so we call the function again. Or a recursive function call is made, and 1 minus 1 is 0, so this becomes HR0. And once we get to HR0, we go back to the function again. Is 0 greater than 0? And the answer is no, so this function terminates. And so the call returns back to HR1, and HR1 it resumes back on line 22, and data is printed. So in this case it's going to print 1, so here's the output 1. And then after line 22 is done, the function is completed. After HR1 is completed, the call goes back to HR2, and HR2 resumes on line 22 where the data is printed. So in this case 2 will be printed, so the output will be 2. And after HR2 function is completed, call returns back to HR3, and HR3 resumes on line 22 where the data is printed, and so 3 is printed, and so the output will be 1, 2, 3. And the way to trace this tree is you go down starting on the left hand side, and let me use a different color to illustrate that. So we start at HR3 and we start on the left hand side, and so HR2 is called, and HR2 calls HR1, HR1 calls HR0, and then we go all the way around, and then 1 is printed, and then HR1 is completed, so we go back to HR2, and then 2 is printed, and then HR2 is completed, so we go back to HR3, and then 3 is printed, and HR3 is completed, and then we go back to main. And again, let me compile this. Again, 1, 2, and 3. Now, how does this recursive function compare to an iterative function? So on the left hand side, I created a count up function because this is basically what our head recursion is doing, is counting up to 3. 1, 2, and 3. On line 11, I call our count up function and I enter the data 3. I commented out our head recursion function so that way we don't get the two functions mixed up. And so let's go ahead and trace our count up function. In main, we call our count up function, and I'll abbreviate that to CU. And every time we call a function, an activation record is created. And so let me trace this. I starts out at 1, and then I is also incremented with I++. And so this condition in the middle of this for loop says if I is less than or equal to data, then increment it. And so the data that we entered is 3. And so let's go into line 28. Is I less than or equal to 3? Is 1 less than or equal to 3? The answer is yes. So that is a true statement. We go to line 30. 1 is printed. I is incremented, and I becomes 2. Is 2 less than or equal to 3? The answer is yes. So 2 is printed. I is incremented. I becomes 3. Is 3 less than or equal to 3? The answer is yes. So 3 is printed. And again, I is incremented. Is 4 less than or equal to 3? The answer is no. So that condition becomes false. It exits the for loop, and then the function is terminated and it's popped off the stack. And if I print this, let me compile and print this, we get 1. We get 1, 2, and 3. In terms of complexities, how does the head recursion function compare to the countout function? As far as time complexities, our countout function has a for loop. So therefore, our time complexity will be O of n. It takes a unit of time to count up. And as far as our head recursion, it's also going to be O of n. Now, in terms of space complexity, if you look at our countout function, only one stack frame is generated. And so the space complexity of our countout function will be constant. It will be O of 1. Whereas our head recursion function, we have multiple stack frames. So we actually create 4 stack frames. So our space complexity for head recursion will be O of n. And as you can see, if space is paramount, then consider writing an iterative loop instead of a head recursion loop. And again, to summarize, a head recursion, the recursive function call is always the first statement in the function. Thank you for watching.